All right. So, yeah, we're at the end of week 3. If you can believe it, after today, we're a fourth of the way done with class. It is flying by. But let's go ahead and look at homework. I know you guys have some questions from that section. So let me share my screen and we will go find those homework problems and take a peek at them. So yes, we'll just, Wes just put on the chat, we're a quarter of the way through your last quarter at the college, or at least for a lot of you. So, oh my goodness. I got a lot closer there than I thought with my guess of page number. Okay, so does this look right? 20, 23, and 28 from this page right here?
None.
Yep.
All right. So let's look at number 20 first. Let me go ahead and write that down, and then we'll go to the whiteboard. Yeah, thanks, Wes. It always throws me when it says will. All right, so we've got 2y dx, and then plus 3 times x squared plus x squared y cubed. That's all times dy equals 0. Okay, so I'm going to quit sharing my screen so that we can go to the whiteboard, but let me just double check that I got this written down properly. I think we're good. Okay, so here is this one, and like always, we want to see if this happens to be exact, because if it is, then life is good. So let's just do the check real quick. So we're going to do my here is equal to 2, and then nx, that's going to equal, well, the 3 is a constant, but then when we multiply everything else out, we're going to get 6x plus 6xy cubed. All right, so clearly not exact. So then the question is, can we actually do this as an integrating factor, with an integrating factor? And remember the two good cases, or the special cases of the in general, are where the difference in these two, when we divide them by either one of these, becomes just a function of x or just a function of y. But you can see pretty easily that that's not going to happen, right? That if we try to divide, we're not going to get this thing in terms of just 1. So what's the other option then? What else do we try to do?
The good old my minus nx time p of x times.
Is it p of x?
That junk.
Ty and then multiplied.
Okay, so we're looking for is the difference in these things, again with the divide by business and all that, can be written as a product of functions, one of which is a function of x and the other is a function of y. Right, so we're looking for a mu that looks like p of x times q of y. And what I really liked, I don't know if you saw this, but Thea was doing like this. There's the p of n, this and that. Yeah, so we know we want to kind of lump it into the 2. And we're looking for some function of x times n minus some function of q times m. So let's rewrite this. So my minus nx, that's going to be 2 minus 6x minus 6xy cubed. And we want that to be some function of x times 3 times x squared plus x squared y cubed. That's our p of x times n. And then minus some q of y times the other one, which is 2y. So this is how we want them to start. We cool with that? So now the question is, excuse me, what are the p of x and the q of y? So here's what I do. I look at what my goal is, and I try to think about what sort of things can I multiply in here to get these pieces. And I'm going to start with the most complex piece, which is the 6xy cubed. Excuse me. So let's look at that. First of all, from this second piece, it's going to be impossible to get a 6xy cubed, because I'd have to multiply by some sort of an x term, which I'm not allowing because I want this to only be a function of y. So if I want to get minus 6x cubed, that's going to have to come from multiplying times the n. And so thinking about it, to get minus 6, I need to multiply by minus 2, because the minus 2 times 3 will get me my minus 6. But then I'm also off by an x. So I'm going to divide by it. So I know that p of x is going to have in it, this might not be all of it, but for sure it's at least going to have a minus 2 over x. So do you guys follow how I got that, or where I'm going with that idea? So I know there's got to be a minus 2 over x. Now, if that minus 2 over x gets multiplied to the other piece, I'm going to get minus 6 over x, and then times x squared is going to give me a minus 6x. So this actually works pretty well for my p of x, because it's going to give me these first, or not the first, the last two terms. So then, can we figure out what q needs to be?
Is it just going to be 1 over y then?
Okay,
oh wait,
so
yeah.
exactly. We
Yeah,
need to
negative
get
1
just
over
plain
y.
old 2. That's the only thing left. So if we need to get a 2 from this q of y times 2 of y, so the y has to cancel, so we're going to have it divided by y. And then I need to make it positive. So it's going to equal minus 1 over y. And so Monty put in the chat, it's a puzzle. And it is. These are totally a puzzle. It's just a question of what do these pieces have to look like? And I always break it down piece by piece. Similarly, I mean, we could have started with the 2, and it would have been pretty clear that we couldn't have got that from this first piece. There's no way we're going to be able to cancel out everything, all the letters, and be left with just 2 if we are restricted to only x's. So that would have suggested, well, let's use that for the y, right? And progress, but basically you just want to attack it piece by piece. But I think we got it, right? We got our p and our q such that this my minus nx can be written as a product of these p's and q's times the m and the n. All right, so far so good? I'm seeing head nods, thumbs up. All right, so now what do we do with these? Like, what was the whole point of finding these p and q?
Finding your mu of x, y, which is e to the integral of p of x and e to the integral of qy.
There you go. So we use these to find our mu. So mu, our integrating factor, is going to equal e to the integral of minus 2 over x times e to the integral of minus 1 over y. So this is a pretty common trick, but once we've got those p and those q, we'll just go ahead and integrate and see what we get. So this first one's going to give us a minus 2 log x. So this is e to the minus 2 natural log of x times e to the negative natural log of y, which is going to give us 1 over x squared times 1 over y. Those negatives, remember that those are going to be powers. We can bring those in as exponents. So we'll have x to the minus 2 and y to the minus 1, so that then the e and the log cancel. So it looks like our mu is just 1 over x squared y. So let's see. Let's take that mu, let's multiply it through, and let's see what that gives us. So when I multiply it to the 2y, the y's cancel, and I get 2 over x squared dx. The other one, all the x squareds are going to cancel, and I'm left with 3 times 1 plus y squared, or 1 over y plus y squared, sorry. So this is what it looks like, and it's going to have the same solution. Obviously, we have potentially different problem spots. Like in the original one, there were no issues on our initial conditions or anything, right? You think about all those functions. Well, I guess there would be if we solved it for dy dx. We'd have to look for stuff. But it's going to be slightly different now. However, you can see pretty clearly that this is exact. Differentiate the first one with respect to y, you get 0. The second one with respect to x, also 0. So since those are equal, we know that this is exact. All right, so let's get our solution. So we're going to integrate these respective pieces with respect to x and y. So the 2 over x squared is going to give us a minus 2 over x. The 3, of course, is a constant. The 1 over y is going to give us natural log of y. And then the y squared is going to give us y cubed over 3. And so it seems to me that that's a good implicit form for this one. You might want to go ahead and distribute the 3 so you can cancel it with that y cubed over 3, but that's not necessary. All right, so how do we feel about 20? Pretty good. So again, the trick really is start by constructing your my minus nx, then literally write it out as a multiple of the two functions and see what you have to do to make it fit. You know, solve that puzzle so you can find which pieces are go where. All right, so good for that one. Then let's go look at the next one. So the next one's going to be very similar. So you should all see my screen, but we're going to look at number 23. So 23 is the same idea, right? We're still going to try to find the integrating factor and then solve it. We just have a different equation this time. So let me go ahead and write the equation up. So we've got y times x cosine of x, and then plus 2 sine of x. So that's our dx part, and then our dy part, we've got x times y plus 1 times sine of x. All right, let me just double check that. All right, I think I got it. So let's go to the board. All right, So we got y times x cosine x plus 2 sine x, and then x times y plus 1 sine x. So we're going to do the same thing as before. We're going to differentiate with respect to y in the first, x with the second, see if they're equal. We know they're not going to be, but we still want to do that anyway. So my, that's going to equal x cosine of x plus 2 sine of x. So then if we look at nx, now this one we're going to have to use the product rule because we've got x times sine x. So we're going to get y plus 1, that's constant, times, well, we're going to get sine of x plus x cosine of x. So that's the derivative of n with respect to x. So then my minus nx, if we subtract those two, first notice I'm going to get an x cosine minus an x cosine when I distribute that 1. So that's going to go away. I'm going to get 2 sine x minus 1 sine x. So that's going to leave me just a sine x. And then I'm going to subtract the other pieces, which were y times sine of x plus x cosine of x. And I'm just going to leave it like that for right now, but we'll adjust it if necessary. All right, so how are we doing? Does that look all right? Please check me, make sure I don't make any mistakes. We don't want an incident like last time where Trey caught that. It should have been an x squared or something. All right, so now, just like before, we're going to see if we can write this as a product of some p of x and some q of y times the respective m's and n's. Okay, so let's just go ahead and do it. We're going to have p of x times n. So p of x times y plus 1 times x sine of x. And then we want to subtract from that q of y times, I don't have enough space to write that here. So let's write it, well, minus q of y times y x cosine of x plus 2 sine of x. Okay, so let's do what we did before, which is fiddle around with these things until we can figure out what they need to look like to get our my minus nx. So my recommendation here is to kind of do what we did before and take structures of ny minus nx and see how we form them from these other pieces. So I'm actually going to start with this last piece, because if I distribute, this would have been a minus xy cosine of x. And if you look down below, the only place where we're going to get an xy cosine of x, that's going to be from here. Right? Like, I mean, I guess I could get it from this as well, but I'm going to have to multiply by, what is it, cotangent? I think cotangent times sine would make that a cosine. So I think that's probably a little bit more complicated than it's going to need to be. So let's try easy first. If it doesn't work out, it doesn't work out. So that tells me that in my q of y, in order to get minus yx cosine x, that means that q of y has to have a 1 in it. Right? There may be more to it, but I know it's got to have at least a 1 so that I get minus 1 times y times x cosine x. Well, let's look and see what that does to the other piece. If q of y is equal to 1, I definitely take care of that last term, but I'm also going to end up with a minus 2 sine of x. Well, let's think about then what we would need in p of x to counter that. If I've got a minus 2 y sine of x, what I really want is a minus 1 y sine of x. So what has to be in px to make it so that I just get minus 1, to basically add in a y sine of x? Let me write it out, because I think me just saying it in words may not help you see it. I want to keep our my minus mx, but let's look at this. So if I do 1 times this, I get minus yx cosine of x. And then I also get a minus 2 y sine x. So this is 1 times that. And we already took care of the minus y cosine of x. But if we look at what else we need, the y sine of x's, we only need minus 1 of them. So somehow I need to get a plus y sine of x.
So would that mean it would have to be
Minus 1/2.
3 over x? Yeah.
Okay, you're very close. So again, we need, this is what we need.
Yeah.
Right? We need that so that we get a total of minus 1. So if we look at the p of x piece, we get a y sine of x with this distribution, but there's the extra x. So we do have to cancel that out. So Thea, you were right about there was an over x, but what it's going to require is just a 1 over x, so that when I distribute through, I get 1 y sine x. So when I add it to the negative 2, gives me a total of negative 1.
Yes.
Yep.
I see.
No,
Yeah.
you would have
Yeah.
been right. What you were going with would have been right if we needed a
Yeah.
positive y
Mhm.
sine x at the end.
That's why I was thinking of. I was thinking of the extra sine x term on accident.
No worries. Okay, so we know that has to be in p of x to take care of the y sine of x. Okay, so think about it. We checked off those two, which leaves us just sine of x. All right, well, the q of y may or may not give us those, but we know for sure this p of x is going to. If we have that 1 over x and we distribute it through, the x's cancel and we're left with 1 times sine, which is actually that piece. So we're good. We've actually got it here. So q of y is going to equal 1, and p of x is going to equal 1 over x. Another really nice thing about these is you can always check yourself. You can always see if we're correct. Just multiply it through and see if we end up with the my minus x.
I got a negative 1 over x for the p of x. Did I see something? Did I miss something there? Do we need it to be negative at all?
I don't think so. Let's just check it real quick. So like I just said, you can always check it. Well, how about we check it? Let's see. So we need 1 over x times y plus 1 times x sine of x minus 1 times y times x cosine of x plus 2 sine of x. Okay, so I'm going to go with my original p and q that we figured out. We're going to put them in here. We'll see real fast if the signs are off. All right, so for this first bit, the x's cancel. So I'm left with y plus 1 times sine of x, which is y sine x plus sine of x. The other piece, if I distribute through, gives me minus yx cosine x minus 2y sine x. And then when we combine that first and last term, we get a negative y sine x. So it looks to me like we match. So I think we're okay. All right, well, there you go. We found the p and the q, which means now we're ready to go ahead and find our integrating factor. So mu then, it's going to equal e to the integral of 1 over x times e to the integral of 1. Well, 1 over x gives us natural log of x. E to the natural log of x is just x. And then integral of 1 is y. So we get e to the y. So our mu is x e to the y. So we'll go ahead and multiply that through. So this is what our differential equation is going to look like now. We're going to have x, y, e to the y times x cosine of x plus 2 sine of x. So notice I just took that y and I lumped it into that x e to the y. Now we're going to get plus x squared e to the y times y plus 1 times sine of x dy. Same story. I took that x and I just lumped it in with the mu. And this thing is now exact. We can check it the same way, differentiate the first one with respect to y, the second one with respect to x. You should get the same thing. I'm going to let you do that on your own, mostly because I'm too lazy. But now we're ready to go. Now we integrate this first one with respect to x, the second one with respect to y. And again, because of the aforementioned laziness, I'm not going to do it. Plus, I know you guys are just going to all throw it into, you know, some sort of online program anyway. Let Desmos do it for you or whatever. But there you go. This one, if you were going to do it by hand, and mostly I'm sharing this for Mikey because he likes to do them by hand, this is going to be integration by parts, probably multiple parts. In fact, you might even have to do the one that Larry calls the eye trick, where after you do parts a couple of times, the same integral you started with shows up again. You have to do a little algebra. So not an easy thing, but again, I know you guys just jump straight to the computer. All right, so is that better for number 23? And I wish I could tell you there's a real systematic way of finding the P and the Q, but there isn't. It all depends on what the form of my minus nx is. Even think about the example I showed you. Like if you go back and you look at your notes and you look at that example that I showed you of doing this, it ended up just being a real quick, easy, simple system of equations because our m and our n were just polynomials, right? And so because of that structure, it was really easy for us to figure out, oh, this one's a equal 1 and b equals minus 1 or whatever. But it all came from what did that system end up looking like. And there, so like I said, there's no rhyme or reason. It is, and you have to adjust. So. All right, so we good for 23. Any other questions before we go look at number 28? All right, I'll share my screen one more time. Let me just move down a little bit so we can see it better. All right, so 28. Suppose A, B, C, and D are constants such that AD minus BC does not equal 0. So you may remember we saw something like that last time with some problem, but again, if you recognize that as a determinant thing, that's just going to make it so that whatever system we end up with works, actually has a solution. Okay, but anyway, so A, B, C, and D are constants, and then M and N are arbitrary real numbers, so they're also constants, but of our choosing. And then we want to show that this differential equation that they provide to us has an integrating factor that's equal to x to the alpha, y to the beta. So basically, some power of x times some power of y, whatever those powers are, they will change. Okay, well, let me rewrite this, and then we'll see what we can do. So I've got ax to the my plus b y to the n plus 1. And then we've got c times x to the m plus 1. Plus d y to dx y to the n. All right, let me just double check this. dx cx dy ax to the m y. Okay, I think we got it. So let's go back over here and see if we can figure out how to go about this. All right, so let's go to the board. So we're going to approach this the same way we always do, which is differentiate the first one with respect to y and the second one with respect to x. So my, that's going to be a times x to the m plus n plus 1 times b y to the m. And then we'll do the same thing with the other one. We'll do n sub x. Its derivative with respect to x is c times m plus 1 times x to the m plus d times y to the n. I really don't like the fact that they used a d here, because that's making me think it's a differential, but it is what it is. All right, so let's do my minus nx. So we're going to get ax to the m plus n plus 1 times by to the n minus c times m plus 1 x to the m minus d times y to the n. So there's our my minus nx. And again, our goal is to write this as a product of these two, where the multiples are functions of x and functions of y, respectively. All right, so let's see if we can do that. So we need to have some p of x times n, or p of x times cx to the m plus 1 plus d times xy to the n, and then minus some multiple q times m, which is the ax to the my plus by to the n plus 1. And now the fun. So here's what I'm going to recommend we do this time. Let's kind of lump them by powers of x and y. So let's see what happens then. So think about like first just power of x. Notice that all we get here is x to the m, which means if you look at our resulting pieces, this x to the m plus 1 can only be x to the m. How am I going to change that from an m plus 1 power to an m power?
Divide by x.
Yep, I need to divide by x. So that tells me that p of x is going to have in it 1 over x. Again, it could be some multiple of it or whatever, but it's going to have to be at least 1 over x. And notice that with the other one, we end up getting the x's canceled, and so we're left with just y to the n. So that's like perfect. If I multiply by some multiple of 1 over x, then that's going to make this x to the m and y to the n, which are the only things that we ended up with as our power. All right, so okay for that? But what I am going to allow, instead of just writing a 1 there, I'm going to call it alpha over x, because it could be a multiple, right? It could be 2 over x, 10 over x, minus 5 over x, I don't know. But I'm just going to leave that as a possibility. Well, let's do the same kind of argument with the other piece. I don't want a y to the n plus 1. So that tells me that q, it's going to have to be some sort of an over y. Again, that's going to make it so that the y's cancel. So this first term leaves me just x to the m, and the other one leaves me y to the n, which is what I want. But like before, I could have a multiple. I could have 2 of these, or 9 of these, or negative 37 of them, or whatever. So I'm just going to call that beta. So let's see if we can figure out what alpha and beta have to be. Let's make sure that they actually do exist, that we would get this guy. All right, so I'm going to try not to erase my my minus nx here for a second, but let's just see if we multiply this by alpha over x and the other one by beta over y, we're going to get alpha times c times x to the m plus alpha times d times y to the n, and then we're going to get minus beta times a times x to the m minus beta times b times y to the n. And now let's just equate coefficients. Let's look at what the powers of x are going to have as a coefficient and equate those, and similarly the power of y. So if I go with x to the m from our p of x minus q y business, we're going to get alpha c minus beta alpha. And what we're going to need is for that to equal the multiple on x to the m here, which is going to be a minus cm plus c. And then if we do the same thing with the y's, we're going to get alpha times d minus beta times B, and that's going to have to equal Bn plus B minus D. So all I'm doing again is I'm taking the coefficients from the first one and I'm equating them to whatever the coefficients are for the second. And I just caught an error. For that first one, the x to the m's, it should be A minus Cm minus C, because they distribute the minus on it. And I'm really glad I just caught that there. Well, there's a system of equations. Two unknowns. I mean, it's really alpha and beta are the two unknowns, right? So if we want to solve for those, let's just see what we would get. Alpha is going to equal beta times A plus A minus Cm minus C all over C. So I just move this piece over so it becomes positive, and then I divide by the C. Then I can fire that into the other equation for alpha, so that we get beta times alpha plus alpha minus Cm minus C over C times D, minus beta times B has to equal Bn plus B minus D. So just remember that all these other things, the A, B, C, D, M, N, those are all numbers that we know. They're going to be told to us. So really the only things we don't know are alpha and beta. Well, now I'm going to multiply everything by C to get rid of that fraction. So I'm going to get beta times alpha plus, or sorry, beta times A plus A minus Cm minus C, and all that times D, minus beta times BC equals BNC plus BC minus DC. So now I'm going to distribute again. So I get beta times AD plus AD minus CDM minus beta times BC. And I know before you go, wait a minute, you didn't write minus CD. I'll explain in a second. That's going to equal BNC plus BC. And again, you might go, well, wait a minute, you didn't write the minus DC. Well, those two things are going to cancel each other out. They're common to both sides. So I'm just getting rid of them at the same time. All right, so we're almost there. I just need to solve for beta. So if I factor out beta from these two pieces, I get beta times AD minus BC. I'll move the other stuff over. So we get BNC plus BC plus CDM minus AD, which then when I want to get beta by itself, we have beta equals all of that crap. So basically, you tell me the values of A, B, C, D, M, and N. I put them in right here, and I find out what that beta is. And again, beta was the coefficient that we have to have in our Q function. So you may remember that it said, you know, given all these values, and then it said something like AD minus BC can't equal 0. Now you can see why, because otherwise we divide by 0. Okay, well, the point is we're able to find beta, which means we are going to be able to find alpha. So let's go back to we needed to show what mu looked like. Nothing like finding out your whiteboard pens don't work. All right, so mu is going to equal e to the integral of, we had alpha over x, and then times e to the integral of beta over y. Well, those alpha and beta are constants. So that means we're going to get e to the alpha times natural log of x times e to the beta times natural log of y, which ends up giving us x to the alpha times y to the beta. And I think, I'm going to go back and look again real quick, but I think it just said show that it has this integrating factor. We didn't actually have to solve it. Yep, it just says show that mu looks like this, x to the alpha, y to the beta. And we did. We just showed that it has to have that form. And we even know more. We know exactly what that beta is going to look like. And knowing what that beta looks like means we can find out what that alpha looks like if we go back to the formula for alpha in terms of beta. All right.
So a lot of algebra, right? And I forget who it was. Was it you, Thea, who said that this is algebra hell?
Yeah, it is, honestly.
And you can definitely see, but I want you to think like mathematicians for a second. For some of you, that's not much of a stretch. For others, it's a painful thing. But think like a mathematician, and think about what we want to do. Mathematicians are all about, how about we do this one time? Instead of all the various different cases, let's just do it once. Well, that's what we just did. We just solved this kind of differential equation for any A, B, C, D, M, and N. I don't care. As long as AD minus BC doesn't equal 0, I now have a solution. Well, not a solution, but I mean, at least we know what the mu is going to be and where we need to go. So this to a mathematician is awesome. Did it once. Yeah, it was algebra hell, but we slugged it out. We got done, and now we've got it forever, right? So mathematicians are all about this. Do it one time, right? Get your answer. Anyway, so is that better for 28?
Way better.
Way better. Okay, so hopefully these gave you a bit of, well, at least showed you a little bit some of the techniques I use to solve these things. But it's all about just, solving that puzzle, as Monty said, right? It's here are your M and your N. We need to multiply them by something that's only X or something that's only Y. What do those have to look like to match this out? And the good thing is that the ones that you see in your homeworks, and if I put one on the exam and stuff, they're going to work out, right? It's not like it's not going to be possible. But there are plenty out there where that's not possible. And so you might be just spending your time trying to do something that's impossible. But at least with this stuff, you know that there's going to be one that works. So you should be able to find it. All right. So we good? Ish for the homework? All right. Well, then what we're going to do today is continue our exploration of applications, things that lead to differential equations. And so just want to remind you what we've talked about so far. So we saw exponential growth, we saw exponential decay, which are really the same things, just with either a positive growth rate or a negative decay rate, right? But then we looked at money, We saw that compound interest gives us a differential equation, although it's really the same as these. So all three of these are really the same thing. They're all the same form, right? Then we started turning our attention to things that didn't follow that model exactly. So we adjusted these models where we had something like we were putting in a certain amount of money every regularly occurring. So we had a constant rate of change in addition to the one that led to either growth or decay. We also looked at Newton's law of cooling, saw that that was one where the rate of change was proportional to the difference in the temperature of our object and the temperature of the environment. And then the last one we saw was a mixing problem where we had a big tank full of water and we were putting in salt water and we were looking for the concentration of salt as time happened. So what I want to do today is I want to revisit the mixing problem because I want to show you one that is a slight variation, but it's an important variation. And this is going to be one where our flow rate in and out are not the same. So that would be our tank is filling up or our tank is emptying instead of the volume staying the same. So we're going to look at that. I also want to revisit Newton's law of cooling where the ambient temperature isn't constant. And if you think about that, that's actually really realistic, especially if we're going to talk about something that spends a lot of time in the environment. Like think about just like the daytime temperatures. Daytime temperatures are not always the same, right? They start cooler in the morning, they warm up into the afternoon, then they cool down, then they warm up, right? You can get something that's fairly sinusoidal. Well, what happens if we put an object into something that's varying temperature, right? So we'll add a little bit more realism to both of those. And then if we still have time, we'll see. I want to get all of you physics people excited because we're finally, for the first time, going to take air resistance into account so that when we throw something in the air, we no longer assume there's no air resistance because we know that that's bogus somewhere like on Earth, right? So you guys are finally ready to tackle some of those problems. And I hate to put that qualifier on there, but you'll see why. There are only certain ones that we know how to do just yet. But the good news is we'll know better how to tackle these later as we learn a little bit more in differential equations. But we are still going to be making an assumption. It's a better assumption than no air resistance, but it's still not perfect. Okay, so let's go to the board and let's revisit. I'm actually going to start with the Newton's law of cooling example, but let's put in a variable temperature, all right?
So Newton's law of cooling, you may remember. And if you don't remember, I'll still go ahead and tell it to you. Kind of looks like this, where we had Q prime. So this is the change in our temperature. It was actually equal to negative K times Q minus, and I forget what I call this. I call it TA. If not, that's what I'm going to call it here. So the A is for ambient. So that's the temperature of our environment. So we saw that this was our differential equation. So hopefully you remember that. It looks something along those lines. And what we did last time was we went with the assumption of that temperature is constant. But like I was just talking about a second ago, that may not be the case. That temperature may actually vary. And if that temperature varies, we have to adjust this a little bit. So, for example, let's say that our ambient temperature varies sinusoidally. Okay, so I'm going to call this a T naught plus Ti times the cosine of some omega times T. So the way to interpret this is that our ambient temperature, there's a baseline temperature. This would be like our average temperature of the day. And then we're adding to it this Ti times cosine. So Ti that's going to be the amplitude of the cosine wave, which is really half of the temperature swing. So if you were to look at low temperature and high temperature, right, you cut it in half, that's your average. That would be this T naught. So in fact, this is, let me just write that. So this is average temperature. And then TI is how far you can go from average, either up or down. Okay, so I'm going to put here, this is 1/2 of the temperature swing. So like, let's say we had high temperature of the day was 70 degrees and the low temperature at night was 30 degrees. Then T naught would be 50 because that's smack dab in the middle. And then TI would be 20 because that's how far we go from the average. And then the omega, that's just going to tell us how frequently the temperature is changing, right? Our period is going to be determined by omega. So if we're talking about it's a daily thing, then we would need to have the full 2 pi happen over 24 hours. So omega would be pi over 12. If this were a yearly thing, then the 2 pi would happen every 365 days. So omega would be 2 pi over 365 and so on and so forth. Okay, but that's really just telling us how frequently it's changing. Well, let's think about then what happens to the differential equation, because we were able to solve this one pretty easily. I don't know if you remember how we did that, but it was separable. You could take the Q minus TA, put it over here. It ended up separable, so it was a real quick, easy solve. But as soon as we do this, where we allow that ambient temperature to change, it completely changes the process of solving this differential equation. Because now we've got Q prime equals minus K times Q minus T naught minus TI cosine of omega T. And this isn't separable anymore. This Q with the cosine of T, we're never going to be able to split those two apart. All right, so does that mean we're screwed?
Not necessarily.
No, not necessarily. I mean, we might be in trouble depending upon how this temperature varies. But in this specific case, no, we're still okay, because look at what we can do. I can move this KQ over to the other side, so we get Q prime plus K times Q, and that's going to equal K times T naught plus TI cosine of omega T. I factored out the minus sign, canceled it. And this is linear first order. So in the language of the letters we used before and all that. So P of X is K. And then G of X is this K times T naught plus TI cosine of omega T. So we would find the solution the way we normally do. We would take the e to the minus P. So that would give us e to the minus K. That would be our Q1. Then we would go to our integrating factor, where U prime is equal to this thing, the other side, divided by Q1. So then we would integrate that. That gets us our U. And then we take that U and multiply it by our original. So I'm not going to bother going there. I'm not going to actually do this one. But you can see what the process becomes. So it's the exact same idea, but it allows for something more realistic. Assuming that temperatures are constant when you're doing Newton's law of cooling is not a good assumption, unless we're over a very short time period. So this opens up the opportunity to do all kinds of crazy stuff. All right, so questions on that? or how things change. Well, okay. So then let's go look at mixture again. And this time, let's adjust the mixture so that we don't have the same amount going in as coming out. So let me first remind you about the mixture. When we did the mixture problem, what we were really looking at is just in minus out, right? We were looking at Q prime. It was, how is Q changing coming in? And how is Q changing going out? And we just did the in minus out. And so when we did it before, we had the same rates, so everything was really nice. But it was basically looking at coming in and going out. So let's try this, but let's adjust it so that our rates in and out, or at least the flow rates in and out, aren't the same. So here's the example we're going to do. Let's look at a tank again. It's like before. Right? Now we've got some coming out. Now we've got some going in. But this is how it's going to play out this time. Let's say we're looking at salt again. We're going to look at salt concentration. But coming in, we're bringing in that same 1/4 of a kilogram. So we're going to have 1/4 kilogram of salt per gallon. And let's say that it's flowing in at a rate of 3 gallons per minute. And I'll also tell you that this tank is 100-gallon capacity. That's what the same tank as we did in the last example, or the example last time. All right, so every minute, 3 gallons are coming in, and each of those gallons contains 1/4 kilogram of salt. All right, but now this time, let's say that it's flowing out at 4 gallons per minute. But I want to answer the same question. I want to get some kind of a function of salt content per time. So it's really the same question as we had before. It's just we're going to get a different function. All right, so are we cool with the setup? See what's going on? So here's my first question, is what's going to happen over time with this tank?
The salt concentration is going to go up, but the overall water volume is going to go down.
Okay, that's a very good answer. We're going to see that it gets saltier. Right, it's going to get saltier, assuming we started with fresh water. So it is going to get saltier, but we're also going to get less over time because we have more leaving than coming in. Right? In fact, how long until this tank is empty? How long is it going to take until this tank actually gets emptied in this scenario?
Is this assuming that it starts out full?
Yeah,
or...
let's go with that. It's a full tank to start.
So 1 hour and 40 minutes?
That's exactly right. Because we're losing 1 gallon per minute. Right? We're removing 4 but putting in 3. So the net result is we're losing 1 gallon every minute. So it's going to take 100 minutes for it to empty. So the hour and 40. So eventually this tank will empty, which means that the function that we find, we know is only going to be good up until 100, because after 100 minutes, basically all the water that's going in is coming out, so there isn't anything in there anymore. All right, well, let's see if we can find that Q. So we're still going to look at this as how much salt is coming in versus how much is leaving. So in terms of how much is coming in, we know that we're getting 1/4 of a kilogram times the 3 gallons per minute. So we're actually going to be getting in 3/4 of a kilogram of salt every minute. All right, so now we want to figure out how much we're losing. And so we want to do kind of the same thing we did before, which is look at what is the concentration of salt in the container itself, and then multiply that by how much is leaving. So again, I'm going to put here just times 4, because I know my flow rate out is 4 gallons per minute. So do you remember how we figured out what we multiplied to that rate? Or can you look back in your notes and see?
It's the content of salt divided by the volume.
Yeah, so it was how much salt divided by volume, right? So it's the same kind of thing. It's a mass per gallon. So before we multiplied it by Q over 100, right? Because there's Q kilograms of salt and it was 100 gallons. Except this time, it's not going to be 100 on the bottom, because it's not always 100 gallons.
Oh yeah, the total volume is changing.
Okay, so the total volume is decreasing. So what we need here is a formula for volume with respect to time.
Would it be 100 minus T possible?
And that would be exactly what it is. It's going to be 100 minus T. Because every minute we're losing 1 gallon. So that's why we're going to subtract T. If it was every minute we lose 2 gallons, that'd be 100 minus 2T. If it was every minute we added 3 gallons, it would be 100 plus 3T, and so on. But it's still concentration. It's still the amount divided by the volume. It's just our volume is variable. All right, so that's a little funky, but there's our formula. That's what we're going to get. All right, so this is a little bit different, because the last one, when we did it last time, we didn't have any functions of t, so it was just constant coefficients. However, this thing is still a linear first order. Because if I move this bit with the q to the other side, notice that this is exactly the form that we're used to for the linears. So let's go ahead and finish this one out. Let's go ahead and practice solving the first order linears. But before I do that, any questions? We okay with where we got? All right, so we got to find our integrating factor, right? So we're going to start with y1 or q1. So q1 is a solution to the homogeneous. So if that was equal to 0, that would equal e to the integral of -4 over 100 minus t. So that's going to give me a natural log. So we're going to get 4 times the natural log of 100 minus t. which is equal to 100 minus t to the 4th.
Wouldn't it be 1 over 100 minus t to the 4th? Because it's a negative for a natural log of 100 minus t.
The negative got canceled with the negative from the 100 minus t. So I'm pretty sure we're good. But thank you, JP. Thanks for checking me here. All right, so then we know that u prime is going to equal 3/4 divided by q1. So that's 3/4 times 100 minus t to the minus 4. So if I integrate that to figure out what my u is, well, I raise that to the minus 3. I divide by minus 3. But then I also need a minus sign from inside. So all those signs are going to cancel. And I'm pretty sure that that gives me u equals 1/4 100 minus t to the minus 3 plus c. All right, so then what do we do with that u?
Multiply it by Q1.
Multiply it to the q1. And so what we end up with then is that q is going to equal 1/4 times 100 minus t plus c times 100 minus t to the 4th. So if you go back and you look at your notes, this is way different structure to the solution. The solution last time was just some constant minus an exponential, a negative exponential, which is a way different looking creature than this one. And in fact, we could go ahead and figure out what C is if we were told initial condition, right? Like if we were told at the start there was no salt, you let Q equals 0, T equals 0, you can find your C and whatnot. But I want you to look at this. What happens to this equation as T goes to infinity? The actual answer is you don't care. Why don't we care what happens to this as T goes to infinity?
Because it's just going to empty.
Right, it's going to empty. And remember how long it took for it to empty?
An hour and 40 minutes.
So it was T equals 100. I don't care about this once T gets beyond 100. Because once T gets beyond 100, this doesn't apply anymore. And notice what happens when T equals 100. What do you get for Q?
0.
You get 0, which we should get, right? Because in 100 minutes, there shouldn't be any salt in the tank because there isn't any water in the tank. So what we're going to see with this one, it's actually a quartic, a T to the 4th. And you hopefully remember that T to the 4th, they do have a max Like if you go and you look at end behavior,
You remember your polynomial dance where evens go either both up or both down, right? Odds, you go one way or the other. So this is an even degree polynomial. It's got a, well, it's going to end up getting a negative c to make it work out. So it looks something like this. Well, we get a concentration of 0 at the start. It goes up, but then comes back down. So it turns out that this one's a little bit funky too, as opposed to what we saw before with the concentration kind of coming up and leveling off. This one, it's going to reach a maximum amount of salt, and then it's going to start going down, because even though the concentration got higher, it's being removed faster. And remember what Q is the actual amount of salt. It's not the concentration. It's not salt per volume. It's just the amount of salt. So there is going to be a point at which there's the most salt in there, and then that number goes down because we're removing it faster than we add it. All right, well, another variation, but led to a completely different structure of an equation. And that's kind of what I wanted to illustrate really with these two examples, is how just changing one bit can completely change the solution. And I don't mean just like by a coefficient, or yeah, if we had made it so that you're getting a half a kilogram instead of a quarter kilogram. No. Like, I mean, a completely different looking kind of function, because we're in a completely different scenario, right? So what if it had been the other way around? What if we were taking out less than we were putting in? So like in this case, we were putting it in at 3 gallons per minute and leaving at 4 gallons. What if it was the other way around? We were putting in 4 gallons and losing 3. Well, we'd still have to approach it with changing volume. This time it would be added. And I'm sure it's not going to surprise you at all that we're going to get a completely different structure because we're in a different scenario, right? And there still is going to be some sort of a max in terms of our time period, because our tank's going to fill. But you can actually still have these things that are quote unquote infinite if we're talking about like an ocean. Like think about if we're going to be looking at the amount of salt in the ocean, and you know, is there more water going into the ocean than being brought out? Maybe. Right now it looks that way, right? Sea levels are rising. But is there going to be a limit to that? I mean, yeah, eventually, but that T so far out in the future that for us, it's not going to matter. So you really can have things that act like they can go on to infinity, even in the real world. So anyway, fun fact. So mixture problems, this is one that if you talk to Larry, and I imagine there's not a lot of that going on right now because he's, you know, we're not on campus, but Larry will call this a pond problem, as will I, because kind of the classic is you've got a pond and there's a pollutant coming in and you want to determine how much pollutant is in there. Well, it's a mixture problem, just like this. You've got stuff going in and going out. So if you hear me say something is a pond problem, it's a mixture problem. And you can actually generalize this to just about anything. A savings account is a pond problem. You're putting in money. The money is growing. You're taking out money, right? Anytime you've got stuff going in and out, it's a pond problem in this mind. But basically, it's just look for rate in minus rate out and go from there. All right, so how we feel about that one? We cool with that?
Yep.
Okay. So I'm tempted to call it for the day, but at the same time, I know you guys are desperately wanting to see this. How do we deal with air resistance? So I think what I'm going to do is just sort of start giving you the preview, because this will make sure you come back on Monday, right? Because you're gonna want this. For all of you that were like, no, we can't ignore it. Let's talk about why this is even going to come about and how really Newton's second law leads to differential equations. Okay, so I'm just going to give you kind of the background of the mechanics. And for those of you who have not taken the physics, don't worry, I'm not going to go too heavy, but I'm going to give you enough so that you can actually do the differential equations. So let's go to the board.
Okay, so let's talk about Newton's laws, specifically the second law. So you guys all remember that, right? I hope.
Yes.
It's the granddaddy of them all. It's the good old F equals ma. So Newton's second law, it basically just says that if you add up all your forces, then you can determine your acceleration, because your acceleration is proportional, and the proportionality constant is actually the mass of the object. So we've got our force is equal to mass times acceleration. So let me just rewrite this real quick instead as ma equals, and I'm just going to call this big F. It's a force, but this force, it's going to be a function of t and other stuff. And up to this point in physics, you've only dealt with those that were a function of just t. So your force may have changed with time, but that was it. You didn't look at it in terms of other stuff. Okay, well, now we're going to allow for some other stuff. So first of all, just to help us here, because I think we'll get confused with the letters, I'm going to let just y be our position. I know you're used to using x as position, but I'm going to use y just because I think it works a little bit better in the context of differential equation. So basically now, let's just say that our force can depend upon time. It can depend upon where we are. That should totally make sense, because think about something as basic as we're looking at forces on an airplane. The forces on the airplane depend upon where it is. If it's higher up, there's going to be less gravity. Right, so already right there, you can see that there's something that depends on position. So we'll allow forces to depend on the position. But what if we also want it to depend on, say, velocity? Because there are going to be some forces that are affected by velocity. The aforementioned air resistance is one of them. Think about it. The faster you go, the more air resistance there is. You guys already know this. You've experienced this. Like, think about when you're riding a bike. If you ride slowly, it doesn't feel like there's much wind blowing you in the face. Where if you ride quickly, there's a lot of wind, right? So that wind is air resistance. So it's quite possible to have our force be a function of velocity, right? And it could be other things, but let's just basically start here. We'll go easy. That this force could depend upon time, your location, and how fast you're going. Well, this velocity, that's also known as the derivative of y. So we've got, instead of a function of t and y and v, we could call this t and y prime. And acceleration is also related to y, and it's the second derivative. So Newton's second law pretty much shows you where the differential equation is coming from, and the fact that acceleration is a derivative, right? It's a second derivative of position. So Newton's second law leads naturally to second order differential equations. All right, well, that's great and all, except we don't know how to solve second orders. At this point, we're still restricted to first orders. And this is why earlier when I mentioned the air resistance and I was like, oh, you'll be able to solve these, I said, well, some of them. because the general, we don't know. We don't know second orders yet. We will. I think that comes out in the next chapter, in chapter 5. But some of these we actually can do with what we know right now. So let me show you how we can change this so that it is a linear, or a first order, differential equation. Okay, so remember when we had this t and other stuff? Let's say that other stuff doesn't include y. So we're not going to base it on position. We're going to look only at things where the force is dependent upon the time and how fast we're going. So let me just rewrite this again. So let's just say we've got F of t and v. Well, acceleration is still related to velocity. It's the derivative of velocity. So this now is going to look like m times v prime equals f of t and v. And this one, my friends, is first order. And that we can solve. So as long as we can represent the force as a function of only time and velocity, this turns into a first order differential equation, and we can solve for velocity. Right? That's what we're going to do with these. This one we're going to solve for velocity. Now, if the ultimate goal is actually position, that's not that big of a deal, because if we can get a formula for velocity, we should be able to go and get a formula for position. We're just going to have to integrate one more time. So that's where we're heading. We're going to start looking at what are those forces that we can think of as functions of just t and v. And like I mentioned, drag is a great example.
So one of the assumptions we're going to make next time, because this is where I'm going to leave us, but one of the assumptions we're going to make next time is that our drag is proportional to velocity, or proportional to the square of velocity, or something along those lines. And we're going to be able to start seeing what happens once we allow for air resistance. And this should make all of you physics types happier, because we're no longer going to have objects that when they fall keep speeding up forever. We already know that doesn't happen. In fact, I'm sure you've heard of the term terminal velocity, right? That phrase, terminal velocity, that's the maximum velocity a falling body will get as it's flying through the air. And we'll see that. We'll see where that comes from once we allow for drag. All right. And so this is also going to apply for things moving in any kind of fluid, right? Not just air. So if we're going to talk about a rock that's falling in the lake, as it falls through the lake, it's getting slowed down by frictional forces with the water. We're going to be able to describe it in a similar way. All right. So I'm going to end us here. Let me just go ahead and hit pause.